There's something even more foolish than diving into an empty pool, and that's targeting our Sun, an ordinary star of spectral type G. Since there are more than 100 million like it in the Milky Way, diving into this most ordinary star will lead us to an extraordinary fate. This video is proof of that, through the trial by fire and solar wind that occasionally manifest as we get closer. These gusts of ejected plasma flows make the Sun lose about 1 million tons of matter per second here. For us, the main issue isn't density, but the speed of the particles, as this hot plasma travels at about 450 kilometers per second, enough to erode comets and probably a bit of our ship's hull too. After 3 months of non-stop space travel at 70,000 kilometers per hour, we finally reach the star's upper atmosphere. The streams of particles hitting our hull are still very sparse, but their temperature is increasing. It's insane. We are entering what is called the crown of the Sun King, the kind of saddle no one would want to put on their head. This layer, larger than the Sun itself and surrounding it before gradually dissipating into space, extends nearly 10 million kilometers above the surface. And this region could very well cook us instantly, like stuffing. Count about 1 million degrees during periods of low activity and up to 4 or 5 million when our Sun gets agitated. The question of why it's hotter here than on the Sun itself, by a factor of 1,000, remains a burning and unanswered one. One thing is certain, this journey, destined to end badly and just begun, is likely already over. So let's continue in this corona, the stage for miniature solar eruptions. Here, thermal bombs occasionally explode when the magnetic fields that shape the corona cross and realign. Our onboard electronics are put to the test by intense magnetoacoustic waves coming from the photosphere. We could fear serious sunburns, even though we aren't really touching it yet, because the density of this plasma of stripped atoms is still very low, about 1 billionth of the density of Earth's atmosphere at sea level. The base of this region is the site of a chaotic and constant movement. Here, spicules form as gas filaments rise from the chromosphere. Like many fiery mains, with locks about 500 kilometers wide and almost 10,000 kilometers high, it's deadly yet beautiful. Occasionally, solar eruptions break out, reaching heights on the order of the distance from the Earth to the Moon. There are also coronal loops here. These arcs, which emerge and then plunge back into the star, are connected at both ends to sunspots and don't let us appreciate their true size, unless we put our planet beside them for scale. We're back in the chromosphere's thin layer, where temperatures have dropped to 100,000 degrees. And over the course of 2,000 kilometers, as we get even closer to the star, they will drop to just 3,700 degrees. It's now so mild that in this thin layer, at the base of the chromosphere, you can find simple molecules such as carbon monoxide and even water vapor. Meanwhile, pressure rises and the plasma gets a bit denser. We are now facing the photosphere, which is the Sun's surface. The main part of this zone, about 500 km thick, is extremely powerful, with an average temperature of 5,700 degrees. As for the sunspots that can appear there, their temperature is around 3,500 degrees. And it might be tempting to think that it could be a good idea to try to use one of them as an entry point. They remain in place for about 2 weeks and are easy targets, as most are twice as wide as Earth. But that doesn't consider that these colder zones result from intense magnetic activity accumulating there. Attempting to enter these structures that cause solar flares and storms risks dying spectacularly. It's better to focus on smaller and hotter structures, which give the photosphere a granulated appearance, like orange peel, shaped by the constant movement of rising hot plasma cells, surrounded by cooler material that sinks back into the star. Each of these small spots is about as wide as France. We're about to dive into one of them. Beyond the photosphere, we've technically entered the Sun. At what moment? It's hard to say, since a star lacks a true surface. The photosphere is a transition region where we go from a relatively transparent gas, a bit like glass, to an opaque and dense enough zone that visible light can no longer pass through. And even though we're now inside the star, it's literally impossible for us to see any farther than the tip of our nose, burned by an environment where the temperature now exceeds the melting point of tungsten, the metal most resistant to high temperatures, by more than 2,000 degrees. Here, nothing solid that we know can exist anymore. But since we ended badly from the start, we might as well keep diving in a different form. In this hell, heated white hot and plunged into total darkness, endowed with a vision and a special power that is for the center of the sun. A passport. His name is Onsen Fu. We say we're not dead. We're now moving into the convection zone. It's like in lava lamps, only prettier and a bit overcooked. The temperature rises as we descend, battling the current and being tossed by massive convection cells, whether they're moving up or down. Diving at 1,000 kilometers per hour, it takes about 5 days to go from nearly 6,000 degrees to around 2 million. We have reached the top of the radiative zone. Solar matter is now so hot and dense that heat transfer occurs only through thermal radiation. This is where plasma bubbles get energy to rise to the surface. All matter around us emits X-rays, gamma rays, and high-energy photons. And since we are directly part of this atomic soup, ourselves included, it's both very deadly and very beautiful. But just to make sure that going even further is a really bad idea, let's keep diving in. Traveling at the speed of a lean airplane, it still takes 13 days to reach the core, the nucleus. This is the last stop. Everyone off. The pressure here is 200 billion times higher than at Earth's sea level. The density is 15 times greater than lead's. We've also just endured intense heat. The temperature now shows 15 million degrees on our dashboards, which have long since disappeared. In this region, the sun becomes thinner. Every second, it converts 600 million tons of hydrogen into 596 million tons of helium, with the rest becoming energy. And since we're present there, we too will help make the star shine. Because the infernal conditions reigning in the core will eventually overcome the nuclear repulsion forces that hold together the nuclei of the hydrogen atoms that once belonged to us. And here we are, in turn, partly converted into energy, assuming 100,000 of you were curious enough to take a one-way ticket to the sun. The combined fusion of our late hydrogen atoms will release here an amount of energy on the same scale as what all of humanity consumes on Earth in a year. The photons produced by the decay and fusion of our matter will be constantly absorbed and re-emitted there, absorbed again. In a constant billiards game, moving randomly, a path to the surface they should reach after 10,000 to 170,000 years before shooting into space. In a distant future, maybe our descendants will look up at the sky and say, when some of those rays reach them, look how beautiful it is. It's like 100,000 foolish grandpas and grandmas all got skinny by diving into the sun.